Go.
Okay. I think, let's hope it works.
Yes.
If it starts getting blurry, let me know.
Okay.
Okay, so we want to talk about absolute value equations and functions. Your basic absolute value functions, just y equals absolute value of x. And I assume you know how absolute value works. It just gives you the number itself. You know, I guess it's worth writing down the definition. You actually have a split definition. Absolute value of x is equal to x if x is positive, greater, not negative, greater than or equal to 0. It's equal to negative x if x is less than 0. So for example, since negative 3 is less than 0, you go to this definition, which tells you that the absolute value of negative 3 is negative 3, which is 3. Now, if x happens to be greater than 0, then you just have x. So your absolute value does exactly what you expect it to. So if we do the table, it's very straightforward. We're going to get 2, 1, 0, 1, 2. And the graph and I didn't put 1/2 in here, but I easily could have. And officially the 1/2 does go in here. But so here are the points, and we also have the point 1/2, 1/2. And they just lie along 2 straight lines, meeting at the origin. And we'll call that a vertex. So there's the graph of the basic and extended basic function. Okay, well, no big surprise. That's pretty much what we would expect. Now, what if we had f of x equals the absolute value of x minus 4? Well, we could plug in points and stuff, but we don't have to do that. We know from what we understand about transformations that this function is going to shift the basic function 4 units to the right. So here's our basic function. We could take each of our points, each of our basic points, and shift each of these points 4 units to the right. So this point would shift 4 units to the right to here. This point would shift 4 units to the right and end up, say, here. This point would shift 4 units to the right and end up here. And the vertex would shift 4 units to the right and end up here. And we have this out here at x equals 4, extend the x-axis. And of course, we could then shift each of these points 4 units to the right. And then we just go a little further. And we get this part of the graph. Not very well drawn. I had a bad slope there, but I was looking at a bad angle. Okay. So let's let g of x equals 1/2 absolute value of x. Let's see, what's a convenient? I'm going to do x plus 1 minus 2. Okay, well, we can see this as a series of 3 transformations. Didn't really leave myself room. I'm gonna reposition this. I'm going to come over here. So -2 is going to be here. 2 is going to be up here. And am I getting that? Yeah, I'm getting it with the camera. And I'm going to put 2 over here. -2 here. So I'm going to have my points. So here's my basic function. Y equals absolute value of x. Now I have the 1/2 here. So I move all my points twice as close to the x-axis. The y values are all going to be half of what they were. So we have all the y values. And we can do that carefully with coordinates, but here we have the graph. And multiplying by half compresses everything. Now we always do stretches and compressions before we do shifts. If we do them afterwards, we're actually violating the order of operations. So we've done that. And next, we can do the shifts in any order. So I'm going to go ahead and do the vertical shift downwards. We have to move everything 2 units lower. So we take every point and we move it 2 units lower. Let me go down a couple of marks here to help. Okay, so this point is going to go down to here. So it's going to come 2 units lower. I'm going to end up here. I didn't plan where my -2 went very well, but it comes down 2 units. So there's a displacement -2. This point comes down 2 units. This point comes down 2 units. So you got a -2 there, -2 here, and then each other point comes down 2 units. Okay, so the blue graph is that Nola? I see Nola. Hey, Nola, you hear me? You know your name?
Sorry, I had a delivery and
Well, that was
ballistic. Yeah.
Yeah. I'm glad I got to see Nola in action. Okay, the blue graph that I drew is y equals 1/2 absolute value of x. And then the purple graph takes every y value and lowers it by 2. So that's 1/2 absolute value of x. I didn't say absolute value up there, I should have. 1/2 absolute value of x minus 2. And now the horizontal shift is 1 unit to the left. So 1 unit is about this far. About right? I think so. So I get these points. And I get points here, here, and not too far here. Okay, anyhow, I got these points here, here, and here, and they come along this line. I didn't do that real well. But now there is my y equals 1/2 absolute value of x plus 1 minus 2. There are my 3 transformations. Just to reinforce the idea of transformations, I'm not sure you need the reinforcement, but many of the people who are here right now might well need it. Some people might be having trouble because of the weather too, although we didn't have all that much snow or ice. My wife walked the dog early this morning, and a branch up the road fell, and a branch of a tree down the road fell. There isn't much ice. There isn't much snow at all. I wouldn't think there was any significant weight. So it must have been her influence or something.
In Abingdon?
But I'm sorry?
Do you live in Abingdon?
Yeah. Yeah, right here in town. And I was sleeping peacefully, and I heard a beep, and the power went off for just a second. Came right back on, but it messed up my alarm, so I got up too early. It was okay. Okay, anyhow, there we have it. So anyhow, my point is you don't know just what the snow is going to do. So some people might be, oh yeah, let me also mention, and I need to send out an email. Unfortunately, Canvas makes me send out a separate email for every course. Doesn't give me any option to send an email to everybody. And since I've got like 8 courses, subsections of this course and so forth, it's a real mess. it's hard to send out 8 emails and make sure everyone went to the right class. Just clerically, it's just a pain. And I've got to remind people that we're not having class on Tuesday. We have faculty in service. But don't think that'll be much of a problem. Okay, so anyhow, there we have it. So there's absolute value functions. You can easily sketch graphs. Everything's 2 straight lines. Sometimes they're thinner, sometimes they're fatter, sometimes they're up, sometimes they're down, sometimes they're right or sometimes left. But of course, if you know how to do this with the basic squaring function, which is going to be real important in the next chapter, you know how to do it with this. Okay. Now, I'm going to take just a minute. I'm going to pause this video. The camcorder is going to keep running, so the backup will catch it all. Okay, good. Emily, it looks like you're in. Just a very, very quick synopsis of what we've done. Absolute value equations and functions. Absolute value equation is y equals absolute value of x. Definition is absolute value of x equals x if x is greater than equal to 0, and negative x if x is less than 0. Now we know what the absolute value does. If the number is negative, it makes it positive. Well, that's exactly what this rule does. If x is a negative number, we take its negative, and a negative of a negative is positive. So for example, absolute value of -3 would be calculated here. Well, that's an x that's less than 0. We use this part of the definition, and that gives us the negative of x, which is a negative of -3, which is 3. It's often a confusing definition. And since -3 is less than 0, we're using this part of the definition. If we wanted the absolute value of 5, well, 5 is greater than 0, so the absolute value of 5 is just equal to 5. Absolute value of x is equal to x, x is greater than or equal to 0. Now, just using the intuitive idea of absolute value or the definition, we can make a table for the absolute value function, make a graph for the absolute value function. It looks like a whole lot like a parabola, except of course, since we're not squaring these numbers, everything's a straight line, 2 straight lines meeting at what we could call the vertex. We then, I was debating between did and then, and I got then. We then got this. If f of x is absolute value of x minus 4, by the rules for transformations that we should understand quite well by now, that shifts the graph 4 units to the right. To get the same y value, x has to be 4 units bigger, which is why it shifts to the right. So we have our basic function, and we shift it every point 4 units to the right, and we get this. Now, I didn't do it particularly well. The slope of this should have been equal in magnitude to the slope of this, so it should have been a little steeper here. But you get the idea. Every point shifts 4 units to the right. For g of x is 1/2 absolute value of x minus x plus 1 minus 2. Start with the absolute value function. We always do stretches and compressions first. So we apply the 1/2, and we get the graph of y equals 1/2 absolute value of x. And from the original graph, that means every y value is going to be half of what it was here, which means we move every point twice as close to the x-axis. We then can do the shift. We shift 1 unit to the right, we shift 2 units down. We can do that in either order. So I chose, let's go ahead and shift it down. just because I had more room down below than I have up here. I shifted every point down 2 units and got this purple graph. And then I did the horizontal shift, shifted every point 1 unit to the left, and I got this orange graph. Well, that's what we've done so far. Now, if you're given the graph of an absolute value function, so I'm just going to draw a graph. And then I'm going to draw set of X and Y axes. And I'm going to put 1 here, 2 here, 3 here, and so forth. And up here, I'm going to, let's go ahead and use an equal scale. 1, 2, 3, 4, 5. Okay, so there's 1, there's 3, there's 5, and you can guess where 2 and 4 are. Okay, what's the equation for this function? Well, it appears that the vertex has been shifted from the origin over this far. So if we draw, well, we can draw the absolute value, regular absolute value function. It goes through 1, 1, it goes through 2, 2, and so forth. Okay, and over here, we have the same thing. Now, it looks like this graph is a little steeper than this graph. Now, I might be an anomaly the way I drew it. We're going to actually do this by estimating points. So we see first that to get the vertex from here to here, we have to shift it over this far and up this far. Okay, so we know what our shifts are going to be. This looks like about 1.6, and this looks like pretty close to 2. So we've got our shifts. Now we want to know if we've got a vertical stretch. Well, if the shift is 1.62, then the coordinates of this point here are 1.62. Whatever the coordinates of this point are, that tells you the horizontal and vertical shifts. And then we have this point here, which sure looks like 0, 4. So what we know from the horizontal and vertical shifts oh boy. I keep writing things down without thinking clearly enough. Okay. Y is going to be some multiple. And I'll use A for the multiple. Okay, so now I'll finish what I did. Now we know that we're replacing X by X minus 1.6 in the absolute value function. Then we're adding 2. Okay, this is the form Y equals A times F of X minus H plus K. For F of X equal to the absolute value of X. with h equals 1.6 and k equals 2. What we don't know is A. We know that h is your horizontal shift. That k is your vertical shift. And A is your vertical stretch. For compression. If A is bigger than 1, it's a stretch. If A is less than 1, it's a compression. The absolute value of A is less than 1. And if A is negative, of course, it's a reflection. So A tells you whether you're stretching or compressing in the vertical direction. It tells you whether you're flipping over the x-axis, reflecting through the x-axis. So what we have here is we know the horizontal shift and the vertical shift. We can find A. To find A, zero, 4 is on the graph. So 4 should equal A times the absolute value of x minus 0 plus 2. And it's not x minus 0. Be nice to be able to hook up electrodes to my brain and see what goes on when I do that. It's 0 minus 1.6. Because, of course, x is 0, y is 4. This has to be 0, and this has to be 4. There's an equation we can easily solve for A. We get 1.6A plus 2. So that 1.6A equals 2, subtracting 2 from both sides. And A, make sure I can see this, equals 2 over 1.6, which is like 20 over 16, which reduces down to 5/4. And I'm not going to do all that arithmetic. Partly because I'd probably make a mistake, but also don't want to distract from what's going on here. Okay, got to assume that you can solve this equation for A. So A is 5/4. Well, now we know A, so now we know our model. So now we can say y is in the form A, f of x minus h plus k. So y equals 5/4 x minus absolute value of x minus 1.6 plus 2. Okay, so if you're given a graph, and you will be in the homework, figure out where the vertex is, understand why that's the horizontal and vertical shift. That's your h and k. Then take a point, estimate the coordinates of whatever point, and take this form with your horizontal and vertical shift and solve for A. That's the process. Okay. Now, there are other types of equations that arise. And might as well just use the board behind this one. Let's just take, it was 5/4, absolute value of x minus 1.6 plus 2, the equation we just got, and solve. F of x equals 3. Okay, well, that equation is then (5/4) the absolute value of x minus 1.6 plus 2 equals 3. We multiply everything by 4. Once you get used to that, if you got denominators, multiply them out so they don't get in your way. So that means multiply both sides by 4. Now, last time I went through a lot of details. This time I'm just going to give you the result. I think you can multiply every term of this equation by 4. You get this. And then you subtract 8. Now, let's say multiply by 4. That means multiply both sides by 4. Every term on both sides is multiplied by 4. Okay. Now, things just blurred there for a minute. Let me know if that becomes a problem. And then subtract 8 means subtract 8 from both sides of the equation. And that 8 will go to 0 and not have to be written. And we get then 5 times the absolute value of x minus 1.6 equals 4. So that absolute value of x minus 1.6 equals 4/5. Now, what this means is that either x minus 6 is equal to 4/5 or it's negative 4/5. Okay? So there are two ways this can equal 4/5. One is that whatever's inside the absolute value sign is 4/5. The other is that whatever's inside of the absolute value sign is negative 4/5, which means that we have two possible solutions here. We have one solution that says, okay, well, if x minus 1.6 equals 4/5, then the absolute value of x minus 1.6 equals 4/5. There's another way we can get this, and that is if x minus 1.6 equals negative 4/5. Okay. Now I want to continue working things exactly with fractions rather than converting to decimals and bypassing the very necessary operations we need to work with fractions. And we're really going to need the next chapter. Okay, fractions, which is like fraction operators, and depending on the polynomial, some of them are pain, but not that difficult. So I'm going to convert this to x minus 8/5. I went ahead to think about that, but it did. X minus 8/5 equals 4/5, or X minus 8/5 equals negative 4/5. Now, what have we enforced? What I keep saying, you got denominators, multiply everything by denominators, by common denominators. You're going to get 5x minus 8 equals 4, or you're going to get 5x minus 8 equals negative 4. And then this gives you 5x equals 12, so that x is 12/5. And this gives you 5x equals 4, so that x equals 4/5. There are our solutions. Then, of course, 12/5 now, we're going to compare our solutions with our graph. Okay, so it is always good, if you're going to look at the graph, to have the numbers in decimal form. Make sure everything's visible. So this is 2.4, and this is 0.8. Now let's go back to the graph and see if those solutions make sense. Okay, first of all, our equation is f of x equals 3. Well, I've had you do estimates of this nature from the very beginning of the course. This says that f of x equals 3. See what color I haven't used up here. Okay, I haven't used blue, it shows up real well. Okay, so here is the line y equals 3. And here is the graph y equals . Now I've got a problem with notation. I let f of x be my absolute value function. And now I'm letting f of x equal this mess. Okay? We've got to do a little editing here. The only place I've used the f is over here twice. And then I just used it here. I'm going to change the name of this thing to g of x, since I already used the letter f for the absolute value function over here. I didn't anticipate this, should have. Okay, so now this is going to be our y equals g of x, and g of x is now this function that we just solved, g of x equals 3. So what I was going to say is, here's a line where y equals 3. Here's the graph of y equals g of x. And g of x equals 3. For this point and this point. Y equals g of x, y equals 3 here and here. So g of x equals 3 at these points. And now I'll blindly just drop a couple of line segments down here. And things aren't going to work out as well as I'd hoped, because Can't do that really all that well, but these 2 points are the solutions. This and this here and here. Okay, well, what are the estimated coordinates here? An honest estimate tells me that that looks like about 70% of the way from 0 to 1. So that looks like about 7.7. That looks like about 2.2. So my estimates of the x values here and here, x equals 0.7, x equals 2.2, approximately. Now again, those are honest estimates. I didn't fudge them. I drew my graph, I did my estimates, and there's what I have. Now, does that match my solutions? I think it's pretty good. I think we got 0.8 and 2.4, something like that. Yeah, 0.8 and 2.4. Estimates are 0.7 and 2.2. Okay, so these compare pretty well, convincing me that maybe I solved the equations right for a change. Okay, maybe, maybe not. Now, that's a graphical estimate. I've emphasized graphical estimates from the first day. There's a reason for it, because it gives you a picture of what this equation means. Right here is a picture of this equation and its solution. And it's important to have those pictures. It can be important. It's not just a matter of run through a bunch of algebra steps. It's a matter of understanding what this means. It's a matter of understanding what the graph tells you. Okay. Well, this is what the graph tells you. 0.8 or 12/5 and 4/5 back in here. And I can also then check by plugging these in. So I have 2 checks, which means that I'm less likely to make a mistake. Now, there's a great big deal going on today in space, which is this new rover is supposed to land on Mars, and we're supposed to get confirmation in almost exactly 2 hours. It's 1:36. We're supposed to get confirmation at 3:35. Okay? So in an hour and 59 minutes and 14 seconds, according to my estimate, we should know whether that rover managed to get on Mars. And the big deal about the rover is it's a helicopter, it can fly around. We've been stuck with things that crawl around maybe 10 feet a day. Now we got something that can fly all over the place. Well, it can't fly that far, but it can do a lot more than a ground rover. So it's a great big deal. There are 3 spacecraft right now, one from the United Arab Emirates and one from, where's the other one from? Is it Europe? No, it's China. Yeah. And ours all got to Mars on within a week of each other. The other 2 are already there, but they're orbiting. They're not landed yet. So ours is going into orbit, and now it's ready to land the probe, and it's a great big deal. So when historians look back at my work here, they'll have a perspective on the day. Not that anybody's going to look at this. Okay. If they do, some of you might show up. You might be historical figures someday. Well, yeah, not worried about that. Just trying to get a little mathematics into your heads. Okay. The reason I mentioned that is that in this case, we have two ways of checking ourselves. Now, back in the early 90s, back when I was still an old guy, but not as old as I am, and y'all probably hadn't been born yet, but back in the early 90s, we sent another big deal spacecraft to Mars. And instead of going into orbit, it just plowed into Mars. Didn't do Mars any harm, but it was real bad for the spacecraft. Plowed into Mars at 10,000 miles an hour, something like that. And why did that happen? It's because somebody put a quantity in there that was in kilograms instead of pounds, and they used the wrong units. Very, very simple, trivial error. Why are they even confusing the units? Why didn't they just start with metric units or English units? It wouldn't have mattered. They'd have gotten it right. Metric units are a little easier to do arithmetic with. English units are a little more intuitive. It keeps subdividing things in half. Don't know why that happened, but that was some billions of dollars and very inconvenient. And set exploration of Mars back a few years. And it's because they didn't have enough checks. They didn't check their work. That's why I emphasize check your work, because you can make a big bonehead error. I'm sure people lost their jobs over that. Probably the supervisors more than the people who entered it wrong, because the supervisors are responsible for making sure things are done right. Anybody can make that little mistake. It takes a supervisor to let it pass on, okay? And it takes a bad design in your data entry to make that happen. And it's a big deal avoiding errors of that nature. Okay, well, end of that digression, but understand that I really do want you to check things. Very, very important. Okay, now there's more that we can say. We can go over here to the picture. Well, see how I want to arrange these boards. I've got another one here. Okay, what if I wanted to solve that lessons are going to be easy for the first year. I'll do greater than g of x less than 3. Well, that translates 5/4 absolute value of x minus 1.6 plus 2 is less than 3. And well, we do all the same operations, subtract 2 from both sides. I'll first multiply by 4, then subtract 2 from both sides, and so forth. And we get down to and let's see, just to make sure I've got it right. Okay, all the same steps we did before we do to this inequality. The only thing you got to be careful of when you're dealing with inequalities is if you multiply by a negative sign, the inequality reverses. I'm reminding you of that. That's something you should know. Okay, but that's an important property of doing algebra with inequalities. Everything else is pretty much like doing the equality. Okay, now what's this mean? This either means that well, it means that x minus 1 point. It has to be greater than negative 4/5. I'm not going to go into the details of why that's true because we have limited time left. Much as I'd love to go into the details, I had to rave about Mars. Okay. So if we solve this, we see that x has to be less than, what was it? 12/5. And x has to be greater than 0.8. And of course, solving these, we just multiply through by 5, add, subtract, same steps we used with equality. But we do have the inequalities. Okay, well, x less than 12/5, if we graph this on the x-axis, if 12/5 is here, then x less than 12/5 or less than equal, I said less than, it's okay, I'll leave it less than. X less than 12/5 consists of all values in the x-axis to the left 12/5. X greater than 0.8, and I said 0.8. I'm going to do fractions, we'll do fractions 4/5. So if we got 4/5 here, if 12/5 is here, 4/5 is over here somewhere to the left. So here's 4/5. And just use contrasting colors to see how this works. So here's 4/5, and here is x greater than 4/5. Doesn't include 4/5. So where is x is less than 12/5 and x is greater than 4/5? Well, it's got to be in this part, this interval of the x-axis, and in this interval of the x-axis, which means that it's between here and here. It's where these two overlap. So x has to be both less than 12/5 and greater than 4/5. Okay. So 4/5 is less than x is less than 12/5. Or x is between 0.8 and 12.4. Now let's see here. Let's go back to our graph and ask ourselves, where is g of x less than 3? Well, these aren't displacement arrows. Everything down here is where y is less than 3. The points on the graph where y equals g of x is less than 3. Broke my chalk. Okay. Are here, not including the endpoints. The solutions to g of x less than 3 are then going to have to lie on this interval of the x-axis. Now this graph is getting a little crowded. I tend to do that. So the solutions of g of x less than 3 are in this interval. Estimated .7 to 2.4. Our estimate from the and actually our estimate was 2.2 and not 2.4. So we see on the graph the solution of the inequality g of x less than 3, and we make sense of it. Now I'll close quickly and let's see what, if there's any color I haven't used already. Looks like I don't have any yellow over here in the yellow. Okay. It should also be clear from the picture. Anything happen out there to the blurriness or anything? I froze up there for a minute on my screen. Did I freeze up on yours?
Mine also froze, yes. I thought that
Okay.
was on my end.
As long as we're not blurry, I don't mind freezing. Okay. I mean, it's cold down here anyway. I can freeze. Okay. Now, up here is where g of x is greater than 3. Above this line where g of x equals 3, g of x is greater than 3. Here's the part of our graph where g of x is greater than 3. And then down here are the intervals. Where g of x is greater than 3. So these intervals, these solutions correspond to these x values. So my solutions of g of x greater than 3 are here. And, well, how am I going to get around to that? I'm just going to cross some lines. And here. Now you're going to have to see the rules because we're out of time. Not that I'm unwilling to stick around a little longer and answer questions. I want to stay within our time frame. I'll just comment over here. You get absolute value of x minus 1.6 greater than 4/5. This splits into the equation x minus 1.6 is greater than 4/5. And it also, another branch of it splits into the equation x minus 1.6 is less than 4/5. But it's an or because it can't be both. X can be here or it can be here. If it's here, you satisfy the equation. If it's here, you satisfy the equation. And it should be less than -4/5 here. Okay, so if you solve these inequalities, what you will get, and you can read it from the graph, our estimate is then that would be the interval greater than 2.2 or the interval where x is less than 0.7. So that's what you get. If you solve this inequality, what you get is x is greater than 2.4 or x is less than 0.8. So what you've done is you've divided the x-axis, you've partitioned the x-axis, well, you've split it up. It consists of, for this solution, everything greater than 2.4 or less than 0.8. For this solution, everything greater than 0.8 and less than 2.4. And for the solution of the equation, x equals 0.8, x equals 2.4. So every possible x value is in one of those solutions. You solve the equation, you get 0.8, 2.4. Your estimated solution, of course, is 0.7, 2.2. Okay, well, that takes care of these 2 points. This orange interval corresponding to g of x less than 3 is everything between 0.8 and on the estimate 0.7 and 2.2. On the actual between I don't have that, it's 0.8 and 2.4. And then everything else is a solution to g of x greater than 3. Makes sense. G of x is either less than 3, or it's equal to 3, or it's greater than 3. Those are your 3 solutions. Okay, well, hopefully that illustrates something worth understanding about absolute value functions and absolute value equations. And it looks like we made it through without the video blurring. So I'm going to quickly stop the video.